So the question says, again, I'll just repeat this for you. It says we have 3 points, A, B, and C. We also have some special point, which we call the origin. Now, the vectors, which originates from this origin and ends in my point A, B, and C, respectively, we just abbreviate them with this short annotation, little a, little b, and little c. Now, we also given these partitions. BC is partitioned by the point x, BA by the point z, and point y partition the segment CA, and we're given the proportions here. That's all of the information which is given in that question. Now, the actual question asks us to, there are 3 parts in the question. The first part says find the vectors from O to X, from O to Y, and from O to Z. This is a direct application of the subroutine we just developed with you, because we have the partitions and we have to find the vector which points into the point making this partition happening. All I have to do, I have to just just remember my subroutine and just plug in the numbers in that subroutine. Of course, you can, if you don't like the subroutine, you can do it directly. You can just first find the vector cy and then add this vector to the OC, but that's a lengthier way, especially that keeping in mind that we have to do it 3 times in a row. You should appreciate this efficiency the subroutine will give us. And then I think the suggestion will be the correct one. Here it is. That's the relation, either in the longer form or in the shorter form we established with you in our subroutine. So OX, just by using the subroutine, is given by this. Remember, I call this convex combination. So by referring to this subroutine, let me just put it here, by convex combination routine. By referring to this subroutine we established with you last time, I can immediately conclude that OX will be given by this convex combination. Similarly, similar identities, can be concluded for the other proportions. For instance, if I'll take this proportion, AY, and the vectors which are pointing at the ends of the segment, that's the vector OA and OC. Again, I think I can ask for the help from the software. That's the kind of relation we will have for the OA vector. Let's just look at this carefully. It's not a symmetric relation. Look at this 3 sits next to the vector C, because 3, you see, that's how many parts you have in a y vector. So the more parts you have here, the more contribution of this piece of this vector will be in your convex combination. Here it is. More contribution from this piece, less contribution from this piece. Together, these 2 factors, together they deliver one way or another. That's why we call it a convex combination. Similar trick can be done for the OZ vector, right? If I take this proportion, I need the OA vector and I need the OB vector. This is a relation for the OZ, and that basically finishes the part A. I applied my subroutine 3 times in a row. If you don't trust the subroutine, you can do the steps actually this subroutine is hiding, but if you do this at least twice, I think you will realize how efficient, how good to use the subroutine in fact. And that finishes the solution of the question 8, part A. Now, the part B, actually, it's almost identical to what we've done just by now, right? It's again, we're given a point T, which this time splits another segment, X and A. So it's this segment from X to the point A. And again, we're given the proportions in which it does so. So all we have to do, we again need to invoke my subroutine, right? Here's my proportion. I need now the vectors on the sides, which in this time it's vector array, and one of these OX's we found before. So if I use my subroutine, and this time let me do it symbolically first. If I use my subroutine symbolically, that's how my OT vector will be given via convex combination. Look at this. 6/7 contributions of the OX vector from this side, and 1/7 contribution of the OA vector this side. It's the reason for that because we have 6 parts here and 1 part here. The more parts we have on this side, the more this side will contribute to the convex combination. Of course, we need to find the expression for this in terms of my little a, little b, and little c. So I need to sub in the expressions I have for OX. Oops. I need to sub in the expression for the OX and OA. It should be easy. Let me just do like this. If I select this, and select this, the software should suggest the substitution. Yes, substitute OX and OA and OX in OT. That's the sub. And that's the result of the direct substitution without any simplification. Of course, we can simplify this significantly, right? Because we can't. I'm sorry, we can't simplify. We can, of course, simplify this a little bit by expanding this bracket. Let's just do the expansion. If I expand this, is my expansion. And surprisingly enough, if you look carefully at the coefficients which we come up with, if you look at these coefficients, you will realize that the sum of those coefficients, just like numbers with no vectors, is 1 again. Right? Look at this. 3/7 plus 3/7, it's 6/7, plus another 1/7 is 1. It's another sort of a convex combination, but this time which involves 3 terms rather than 2. Even though this time it's harder to predict, it's sort of expectable because point T, it sits within, well, I don't know if you ever heard this term. Mathematicians call this convex hull. It's just like for your general knowledge. Triangle, in terms of linear algebra, which we study with you, and I will probably comment on this a little bit more later. Triangle, it will be what is known as a convex hull because we take the vectors pointing at the vertices of the triangle, and we take all possible combinations with the coefficients always giving in some unity. That's why this is one of the instances of this effect. Oh, just side comment which probably I'll develop a little bit further later. Basically, that finishes part B of the tutorial question 8, right? We just found the expression for OT based on part A.